Good morning. Thank you very much. It's a pleasure to be here. This is, despite the fact that I've worked closely with colleagues in the coal sector in Poland for probably the past 17 years. This is actually my first trip to Katowice, and I'm pleased to be here. I have to say I have two impressions. My first visit, the first is that the sun comes up very early in the morning. But that also allowed me the opportunity to get up and go for a run this morning around Katowice, and it's a beautiful city. So when I leave here after this workshop and the ICE launch, I'll tell all my friends in the U.S. that you have to visit Katowice. It's a beautiful city, and every day it's 20 degrees and sunny outside. So I'm going to talk today about coal mine methane utilization. We've had several workshops in other countries, and I've spoke about utilization of mine gas. Just so happen those countries really don't have much or sometimes any history of using their mine gas. But here we find ourselves in Poland, which in fact is actually historically one of the world's, in my view, one of the global leaders in mine gas utilization. In fact, I believe coal mines in Poland began using methane from their mines, I think as far back as the 1950s and maybe well before that. So there's a lot of expertise here, but I also recognize that there are many international guests. So I hope you get something out of this presentation. So this was my outline coming into the presentation today. I'm going to talk very quickly about utilization technologies, just a very quick overview. And then I was going to speak to actually developing and financing coal mine methane projects, that's part of my background. However, the next speaker is Ray Pilcher, who is going to speak to financing and developing coal mine methane projects. So the good news for you is I'll be able to cut out probably 6 or 7 slides out of my presentation. And then later on, I think there are panel discussions, and I can always give my thoughts there on developing projects. And then finally, I'll actually speak to a project that I worked on in China, where our goal was to achieve near zero methane emissions mining, incorporating both utilization of drain gas, but also utilization of ventilation air methane, which is what Mr. Mattis just spoke about. So basically, very simply, utilization technologies available for coal mine methane are the same technologies available for utilization of natural gas. Power generation and internal combustion engines, power generation and turbines, natural gas pipeline injection, chemical manufacturing, vehicle fuel. There's a whole range of applications around the world where coal mine methane has been used. People, wherever I go, it's not unusual to get the question, what is the best use of coal mine methane? In my view, there is no best use. It's really dictated by the quality of the gas, the quantity of the gas, and when I say quality, I mean the percentage of methane available in the gas versus other pollutants in the gas, such as oxygen, CO2, nitrogen. But it also depends on corporate policies, whether that's the mining company that actually is producing the gas or potentially the project developer that's building the coal mine methane utilization project, or let's say the company, there may be someone out there interested in purchasing carbon credits from the project with very specific objectives for what type of utilization they want. And it could also be impacted by government policy. For instance, in Germany, they've historically had very favorable feed-in tariffs that have really encouraged use of coal mine gas in power production. Or just more broadly, the general market conditions that are available. In the United States, for example, we have a very extensive natural gas pipeline network. Many of the coal mines are located very near these natural gas pipelines, and so it's very easy for them just to sell the gas into the natural gas pipeline. So the Global Methane Initiative has compiled a database of projects around the world. This gives you an example of what those project types look like, and active and abandoned coal mine methane, or active and abandoned coal mines. By far, the largest project type is power, combined heat and power. Generally speaking, because either it's quite straightforward. The gas doesn't require much conditioning, maybe some dewatering, some dust removal, but you can, generally speaking, you can use the gas down to 25% methane. In China, they actually go below that. However, in my opinion, best practice is not to use gas at those concentrations below 25% because you're moving toward or you're in the explosive range. But as I indicated, in some countries, they've had favorable feed-in tariffs for power generation, as well as requirements that any kind of electricity produced from coal mine gas has to be taken by the grid. In other cases, mines are very large electricity users, and this provides an opportunity to use that gas for electricity on site. And in a number of countries, for instance, in China, where I've worked, industrial power prices are very high. So it becomes very economic to develop a coal mine methane project for electric power generation. As I said, I'm going to move through these slides very quickly because I think this is going to be taken up in the next presentation. The one thing I would say is when you're moving forward to develop a coal mine methane utilization project, in my experience, aside from financing and some other small matters like that, you really have to base your project on a very robust data set. You have to have a very clear understanding of what the mine plan is, the mine layout, and especially the future mine plan, including any type of reserve addition. Like Mr. Bruner and probably Mr. Pilcher as well, I think we all use reservoir modeling. In addition to that, we also use statistical analyses to try to project and forecast gas production, both quality and quantity, in order to determine if a realistic project is there, and then what type of project may be best suited for that site. I'll show you this slide real quick. This is a schematic that would show you what we in our UNEC working group believe would be a best practices project. And effectively, it is a project that seeks to achieve near zero methane emissions from mining. It's impossible to ever achieve, in my view, impossible to ever achieve zero methane emissions mining, just because for safety reasons, and then the reality of operational constraints, there will always be some venting somewhere. But effectively, a near zero emission project will probably entail a range of different gas drainage techniques, whether they're in-mine, surface, or a combination of in-mine and surface. I think Mr. Bruner, for example, gave several examples of both where in-mine and vertical wells are used in gas drainage projects, for instance, in the United States. But it would also entail probably several different utilization technologies at the surface. For example, flaring and power production. And then the third point, or the third part of that equation, is the use of ventilation air methane reduction equipment, so that you're doing everything you can to reduce the greenhouse gas footprint of the project. At the same token, you are making use of a wasted energy resource and hopefully generating some revenue or cost savings for your operation. So I'll move through these because these are all project development type slides. So this is a case study of a project I worked on in China. And it was targeted, it was intended to be a near zero methane emission project. The coal mine is located in Shanxi province, China. Shanxi province is the largest coal producing province in China. I think historically accounted for 60 to 70% of coal production in China, and I think roughly is still around 55 to 60% of hard coal production. Many of the mines in Shanxi province are very gassy, long history of a number of explosions, many problems, but also long history of gas drainage there. This is located in the mountains outside Taiyuan City. Taiyuan is the capital of Shanxi province. So this mine is located up in the mountains at an elevation of about 1,600 meters. This is critical if you are planning a combustion-oriented project because when you go to elevation, you may have to derate your equipment. So you have to effectively upsize your project, which would cost you more money. It is a metallurgical coal mine of about 5 million tons per year with a long planned life with large reserves. Before the project began, the coal mine methane use project, there was no coal mine methane use project, but there was a gas drainage system in place. The average methane concentration was probably around 25%. So it was, so there was some drainage efficiency, but it was, but no utilization. So we set out again to create a near zero methane emission project. We were an investor, investment firm, and a project developer. We had a team of, we had internal financing, but we also had a team of skilled and experienced mining engineers, most of whom were British, some Australian, but also we had a team of Chinese mining engineers as well. We also had a team of engineers who were experienced in process engineering and power engineering. This was intended, it was intended to be a for-profit project. I mean, we were looking to make money on this project, not simply just to break even or just use the gas, I guess, quote unquote, for the greater good. One thing I do want to point out with utilization projects is after I went to work for this company, they pulled me aside and they told me that in order for a final investment decision to come through, they were expecting that the projects would return at least 30% internal rate of return, or post-tax 30% internal rate of return. You know, my immediate reaction was, I wish you would have told me that in the interview, because I probably wouldn't have taken the job. It was, you know, these projects can return profit, and many do. You wouldn't have over 200 projects. But, you know, this isn't Google. I mean, these aren't, you know, you're not going to become a millionaire with a coal mine methane project. So you really have to have a realistic perspective of what the rate of return may be. And that rate of return can be 10 to 15 to 20%, you know, really depending on, you know, the energy and environmental commodity markets that you're working in. So what we were looking to do with this project is definitely maximize gas drainage capture. So our mining engineers would work with the mine to improve gas drainage, improve the gas availability, the quantity and quality of the gas. And then we were looking to use you know, whatever technology proved most appropriate to use the gas. And then any surplus gas we would destroy using flaring. Because you could get, at the time, carbon credits, certified emission reductions when this project was in planning were roughly about 15 euros per ton, because this was 2008, 2009. And then finally, destruction of mine ventilation air, and then small carbon credits through capture of waste heat and utilization of waste heat. So the first thing we did, as I mentioned before, is developing a very robust data system and understanding of the gas drainage system and how that could be improved, and including detailed reservoir modeling, but also real-time continuous emissions monitoring systems in both the gas drainage system and on the ventilation system. So we weren't even just taking grab samples, that type of thing. We actually had continuous emissions monitoring systems with methane analyzers, flow meters, et cetera. So the first thing our engineers did was we had engineers working underground constantly with the mine to improve gas drainage. And we found that we could just take some simple steps actually radically improve the quantity and the quality of the gas, including improved borehole sealing and increasing the orifice size in the drainage pump. So those two things actually had a significant impact. What we also discovered, though, was that that our engineers had to remain diligent really throughout the planning and then the operating process, because the project is operating today. And we find that when our engineers turn their attention elsewhere, things start sliding and the gas quality starts sliding. So we found that you have to be really focused, very diligent on continually assessing the gas drainage system, how the boreholes are designed and drilled, et cetera. So the next step we decided very quickly, just because the industrial power prices in China are so high, that we would actually build a power plant using coal mine methane. And China is very power constrained. They actually don't like to see, the authorities don't like to see power removed from the grid. So that was also a government policy priority that fed into our decision. The power plant, based on the gas, the monitoring we had done, we determined that we could build a 12 megawatt power plant. And we sized that plant because what we wanted to do is you want to run that plant like a baseload plant, because otherwise it's just CapEx that you've lost if that plant isn't operating. And one of the biggest problems I've seen in the 17 years I've worked in coal mine methane is people oversize the projects. And then they're left with equipment just sitting there being unused, and it becomes very difficult to pay off the project. So what we did was we determined what the average methane flow rate was, and then we sized the plant to effectively at 80% of that average methane flow rate. And so obviously that means that there's going to be additional methane that's not captured by the gas gensets, the 12 megawatts of electricity units. So that gas then is flared. And those flares are installed early on to both combust the methane and secure carbon credits and generate revenue before the power plant was up and running. And then once the power plant is up and running, those flares can combust excess methane, thus reducing the greenhouse gas emissions of the project. And also when a power plant is down. We use a modular approach of 3 megawatt units. So one of those units could be down for repairs or just for servicing. And so in that case, you can also flare. But the idea is that you're reducing greenhouse gas emissions regardless, but also generating revenue. The third thing we did was, this is a very cold, northern China is extremely cold in winter, and it's even colder in the mountains. So there was a demand by the mine for some shaft heating. So we were able to build a closed loop oil-based system that takes heat off the gas engines in winter, and effectively is used for shaft heating. It generates a small number of credits. It's a pretty small contributor to the overall greenhouse gas emission reductions for the project, But again, it met the needs of the mine, and it also really helped make a case toward a near zero emission project. We do have there is a passive vent for the project because, as I said, sometimes the system is just, for whatever reason, is not prepared to take all the methane, or equipment may come down, but you always have to have a passive vent to move the methane out, just in case. So the project was constructed. It was started up, commissioned and started up in 2009, and then it was expanded to. The initial project was started up in 2009, and then quickly expanded to a total of 12 megawatts. It uses real-time monitoring system that you can get on your iPhone or your iPad or your computer. Has a system of alarms in case any of the equipment shuts down. You have rapid response teams ready to go and fix the problem. We secured very stringent maintenance contracts with our suppliers. In this case, I think it was Caterpillar engines or Jenbacher. Okay, we had 3 different projects in the area, and we used Caterpillar, Dürr, and Jenbacher on the different projects. And I think this one was, I think these may have been Jenbacher engines, I'm sorry. There was a lot of training involved initially to train Chinese staff and foreign staff on the plant operation, maintenance, and monitoring. And in addition to that, has been continual ongoing training. It was absolutely critical that the staff be well informed and understand the technology and the equipment, and really, any operating requirements, any occupational safety and health requirements for such a plant. Information is transmitted through telemetry to a system that basically takes that data and effectively churns out the information required to quantify emission reductions. So those emission reductions can be verified by the UN, by the CDM Executive Board at the UN FCCC. Finally, the final step in this was the ventilation air methane plant. I used to have pictures of it, but I pulled them off. And that's because I'll tell you up front, the VAM plant, the one as Richard described it, we actually installed 2 units because market conditions, when we moved forward to develop the units and build the units, carbon credits were 15 euros a ton. By the time the units were installed, they were basically 60 cents a ton. And it wasn't financially viable to keep the units. We kept the units on site for quite a while, but finally had to destruct the units. Basically, we used 3 years of continuous emissions monitoring data to really understand what the ventilation flows and concentrations would be. We had about a methane concentration of average of about 0.67% methane. In China, the maximum methane concentration is 0.75%, so we couldn't get up to 1%. But these projects, they make money. The more methane that flows through the units that you oxidize, because that's increases the emission reductions from the project. We built and we designed. We working with a manufacturer, a very reputable manufacturer. We designed 2 units and built 2 units, installed 2 units, and actually commissioned and started up 2 units. One was a 35 cubic meter per second regenerative thermal oxidizer, and the other was the exact same design, but we installed a catalyst. So what that actually did was it actually reduced the throughput capacity of the unit. And the holy grail with catalyst and ventilation air methane oxidation is that they will both lower the power requirements for the unit and also the oxidation temperature so that they're less expensive to operate. than a thermal oxidizer. But what we found is the advances in catalyst had really not reduced the temperatures that much. All they did was required to increase the residence time of the ventilation air in the unit to take advantage of the catalyst. So as a result, we had to downsize the units. But one of the biggest challenges with ventilation air methane projects, and hopefully we can, with proper economic drivers, that issue is resolved. But when carbon credits are 60 cents a ton, it doesn't work. But 40% of the costs, the life cycle cost of the VAM project was the electricity cost, because I know in Australia they're trying to, but I don't know of any country in the world that will allow you to tie a VAM oxidizer directly into the mine FSA. You basically have to take a slipstream off the fan for anywhere from 30 to 100 meters. And so doing that, you need centrifugal booster fans to take the air into the oxidizer. And that required about 700 kilowatts for this project. So effectively what this meant was if we ran this project, we would be really generating no revenue, but incurring millions of dollars of cost every year, just because there were no value of the carbon credits. At 15 euros a ton, we would have been making money on that, and they would have been running great, because the units ran well, and it's a tried and there are VAM projects utilizing this technology in the United States. They've operated in Australia, they've operated in China. It works and it's effective. You just need the economic driver to make it economically effective and profitable, or at least break even. So unfortunately and sadly, the projects had to basically stop operation and effectively dismantle. So, but these are pictures of the project. You can see the I don't know where yeah. So that's the flare, enclosed flare. These are the gen sets. It's kind of hard to see, but that's the closed loop, oil system there. So it's, but the project is done very well. These are the carbon credits, if you will, that have been generated by the project, that have been verified by the UNFCCC. So roughly 2.5 million. So it's, and it's also, I don't have the kilowatt hours it's generated, but it's been very successful for both the company, Syndicatum Sustainable Resources, and the mining company. So in conclusion, so with regard to methane utilization, or coal mine methane utilization, the challenge is not the use of the coal mine methane. It's straightforward. It's basically natural gas. It's really, in my experience, it's access to markets, understanding the markets, integrating with the mining operation, and really the adaptability to changes in methane availability, methane concentration, and flow. You really have to be prepared to face a range of issues as you go forward, including changes in mining operations, gas quality issues, if you're selling to the grid issues, public policy issues, and market issues. Every project is unique. Every project has its own dynamic, but you can develop kind of a systematic approach to actually developing projects, and maybe that's something we'll get into later in discussions. Without a doubt, the thing I probably learned more than anything with these projects over time is you have to have a skilled and dedicated engineering team, both for the subsurface work in the mine and on the surface for your project. And your utilization project is really only as good as the subsurface, gas drainage system is effective. So I think, there's over 200 projects out there. They're very viable. It works. It's straightforward. You just have to be, forward thinking and also a bit flexible. Thank you.